Okay, welcome to the last lecture in this series. Hope you've enjoyed it. I've enjoyed doing it. I'm going to pretty much just stick to the lecture content this time. I'll do anything related to the course mechanics separately and get this up and posted. What I'm going to talk about today is something that really links. I don't seem to link immediately, but talk about sustainability, materials, design, and cars all at once and talk a little bit about, I think maybe one of my biases. I'm very pro math, being an engineer. I think there are quantitative ways of making decisions that policymakers should be aware of, and any literate person should. And we do a lot with adjectives rather than numbers, and I really believe decisions are better made when you have a numerical basis rather than just an adjective basis. This is good, every little bit helps, et cetera, et cetera. Sometimes you really should know what little bits really help and what little bits don't help much at all. And it really, when you do the numbers, it's often not very clear what the right answers are. Along this line, let me give you a plug to something else. And I'm going to talk a little bit about sustainability and energy. And this is a good one. There's another book by a guy named David McKay. And if you look at sustainable energy without the hot air, and his website is withouthotair.com. Um, and this is sort of a companion. I'm not going to talk about any of his stuff. Um, but he has a really nice approach to looking at energy. And again, I think this is something that is very accessible for bright high school students that show how math, science, technology all fit together. Not materials based, but very innovative, very good stuff. So I'm not going to talk much about that. That's David McKay. I'm going to talk about one of his, another British contemporary of his who's sort of a hero of mine, Mike Ashby, and I'm going to adopt one of his approaches in this in a few minutes. Um, so first of all, here are the big objectives. Is really what we want to do is just understand how we can design and really choose materials to minimize energy use and maximize sustainability. So how we can make these choices that tell us if we're being sustainable or not. And it's straightforward, but unless you do the numbers, it's not very intuitive. Secondly, what I'm going to do is really talk about what challenges we face when we design automobile bodies. And again, these are great engineered structures that have loads of materials, technology, um, design, processes, welding, painting, all this in there. We'll look at just the highlights of that. We'll look at how design and material selection affect automotive sustainability, and we'll talk also a little bit about how this drives current research in automotive in new automotive materials, processes, and design. And research into new materials and manufacturing is really, really important. It is indeed how I believe we as a society move forward, and it's getting it into manufacturing is important, and very heartened by all of that. If you link this to the news, just yesterday, President Obama announced a big push for next generation manufacturing research, and automotive light structures are highlighted as part of that, and that's part of what we'll talk about today. Okay, first let me start out by acknowledging where the ideas for this first part come from. They come from Professor Mike Ashby, who's at Cambridge. He's probably one of the most influential material scientists going right now. He's done some really, really cool stuff in lecture number 1 or 2, where I talked about materials and log scales. A lot of that came from Mike Ashby's thinking. Um, some of what I'll tell you today is also based on Mike Ashby's thinking. OSU is a user of their approach. We license the software. I may be taking liberties and bringing this to you, but I think it's well within the intent that everybody has in mind here. This is stuff that we want to get out to students, and I think this approach would make great, great high school stuff. A little bit advanced, but after a materials course, you can get there. So this is a key book. This is about 2 years old, Materials in the Environment, and you know, good book. There's also software that goes along with this. I think the software is probably beyond high schools, although they are trying to market this to high schools. There's something called the CES, Cambridge Engineering Materials Selector. And there's some properties of wall charts, and again, I've talked about some of that stuff a little bit earlier, but right now I'm not going to go through this lecture the same way that it's used by the Granta stuff, but and I'm not going to talk about the Eco-Auto tool, but I will talk something about the strategy for materials selection that comes out of this book, and I'm going to give a very brief overview of that. And then what I'm going to do is give a very concrete example as to how this is all applied or can be applied to making decisions on what you would build a next generation car out of, and what is sustainable and what isn't, and talk about how we can systematically treat that. Okay, so again, it's going to be a story along those lines, and it can be lots of computation that goes with this. But again, I'm not a big fan of the approach of people say, well, every little bit helps. Yeah, yes, it does, but sometimes we feel better about these things than they're actually making a difference. And we really have to know where the big problems are, and attack those first. I mean, most environmentalists are very good about recycling. Recycling a water bottle, something like that, which is a good practice. I'm all for that. But the place you probably, for a lot of people, I think myself included, my biggest carbon footprint probably comes from my airline travel. Whenever I get on a plane, um, there's a lot of fuel burned. It's all going into the upper atmosphere, and a big part of that ticket you're buying is for fuel, and that's probably the biggest part of my personal carbon footprint. That's not something people typically worry about. So I think it's important to worry about the right problems, phrase them right, and again, not adjectives, but math are the right way to do this. So again, a great math tool that I love are logarithmic scales, and this is logarithmic scales versus different categories: metals, polymers, ceramics, fibers and hybrids, composites, and so forth. And then this is annual production. So if you're going to really try to worry about carbon footprint, you probably want to worry about the things you're making a lot of. And again, this is a logarithmic scale. Every time you kick up, it's an order of magnitude 10 times greater. So the thing we produce the most of in the world are oil and coal, and even more than that, concrete. We make a lot of concrete, and it actually takes a lot of energy to make concrete. To dehydrate these ceramics that react, you've got to put a lot of energy in. There's actually, we'll show on another slide, big carbon footprint associated with concrete. That's something you'd really want to avoid if you could. So we make a lot of that, make a lot of steel, a lot of aluminum, up and coming material, magnesium, very low density, is way down here. And to compare it to steel, to here's one factor of 10, here's another factor of 10, here's another, and here's about a half. So this would be 10, 100, 1,000. So we're making about 5,000 times as much steel as we are magnesium, maybe 3,000 times as much steel. So it's a really dominant thing. So again, we're going to worry about problems, try to worry about the big problems. Concrete, we make a huge amount of, and again, that's probably a place we want to worry if we're going to worry about sustainability. So, and indeed, logarithmic scales show this. So 96, and I think maybe the line might have shifted, but I think you go to here, of the materials we produce, oil, steel, concrete, asphalt, and wood make up the vast majority. Everything else is just about in the noise. That's 96, and a lot of this ends up then turning into polymers. So that's a big part of where polyethylene and the like come from. So again, we could look at this in carbon released to the atmosphere, and this is sort of the volume of material that's produced multiplied by how much carbon is produced by that. And again, steel is a leader, cast iron is a leader, concrete is huge in all of that. Other big ones that we don't think about: paper and cardboard. The process of taking the water out of paper takes a huge amount of energy, and technical material we don't think, I think, enough about is concrete. Huge importance to the environment. Gypsum, I don't think shows on here, is another one that's pretty important. So that's big stuff. So now what we want to do is, I think all of us want to be smart consumers, if nothing else. And this course is really, I think, as much as anything, material science is something that's important for technical literacy. So just let's think about the stuff we buy, where it comes from, where it goes. Always what we end up doing, starting with natural resources, something like iron ore, and we produce a material out of it, or the natural resource could be a tree. We turn it into a board or paper. So natural resources turn into material production. When we do that, we make the material and we make this steaming pile of whatever that is, and that represents emissions and waste. And those emissions and waste include carbon dioxide, NOx compounds, liquid waste, solid waste, and so forth. We want to minimize that, and you're hearing a lot of things about car plants being landfill free and so forth, where any packaging material gets reused and sent back, and that's a good practice and all of that. But still, there's heat waste coming off, there's CO2 coming off, and these are not trivial, and these are things that we can track. So energy goes in. An aluminum, for example, is made by an electrolytic process. So huge amounts of electricity are used to make aluminum. Put in feedstocks, again, sticking with aluminum, bauxite, and so forth. Stuff has to be shipped there, shipped back. Shipping requires energy also. So if you're going to make aluminum and use it in Cleveland, that in principle will always have more energy associated with it than the same process that might be working in Akron to supply Cleveland. You're going to reduce that energy. Also, maybe Akron has a more or less efficient plant than might be somewhere else in the world. So anyway, that you produce a material, you produce a product with that material. That also takes energy. We've talked about casting processes where you end up melting the material, solidifying it to shape. Deformation process. All these things take energy. Welding takes energy. To make a material takes energy. Again, feedstocks. Energy goes in. Transportation's evolved. Big steaming mass comes out the end. We use the product. Again, the product, usually for making something like an automobile, the car uses energy the whole time we're using it. If we have a fuel efficient car, it's going to use less energy than a non-fuel efficient car. And so again, if we have a light fuel efficient car, that's a good thing. But what if it takes us a lot more energy to make that light fuel efficient car? And we'll see in detail that yes, it may. Again, same problem. Resources go in, big steaming pile of something comes out. We dispose of the product. Lots of things can happen with disposal. If you've got just paper, it could end up in a landfill. You could end up incinerating it to get energy. If you incinerate it to get energy, carbon dioxide will also come off. You could reuse it, or you could just, not need it in the first place. Reduce is always the highest order. If you want to be sustainable, reduce. So again, you could combust, you could landfill what comes out, and you could end up recycling or reusing. And that's our life cycle. What we'd like to do is capture all of this in numbers. It's pretty complicated what really goes on, and where things go on matters too. And this is the other option. You could refurbish, upgrade, truly reuse, and then on top of this, reduce is often your best option, but it's hard to go. So far, there hasn't been a real strong reduce lobby. We like our stuff. And what we can do is do a life cycle assessment and see how that treats everything. Okay, so let me skip over this right now. So this is one of the slides I think I expected to pull out, but the point of this is there is a process for doing a formal life cycle assessment. As with resource consumption, emissions inventory, impact assessment. I'm going to show you a different way of skinning this cat that's developed by Mike Ashby that I think is a lot better because it's not as time consuming and not as expensive. And after you actually work through it a couple of times, it is, I think, quite a bit more intuitive, although you do need to put numbers into this, and like any accounting process, be quantitative about it. And this is quantitative, as we'll show you. It's probably more detail than we want. So we need some sort of eco audit. We'd like to find out how energy comes in and what comes out. Like to distinguish the life phases. And this is the key that we're going to work with. We're going to figure out how much energy is used in each particular life phase, and we can make plots that are very similar to this, either based on energy or with respect to CO2 emission. So first of all, we have a material. We have to take that material, and let's consider aluminum. We're going to make something out of aluminum, which happens to be my favorite metal. Everybody should have a favorite metal. And what we do is bauxite is mined. It's basically an aluminum oxide, a little other stuff in it. That's mined somewhere. That bauxite is shipped somewhere, and then an electrolytic process is done. It's basically a process that's done at high temperature where electricity strips the oxygen from the aluminum, much in the way Jerry Frankel talked about in this lecture series of it's a reduction process. And with that, energy is required, and a lot of energy is required to strip the oxygen off of aluminum. And that's something we call an embodied energy, and that's how much energy it takes to make the material. We might manufacture that into something like a truck wheel. That could happen by a casting process. Casting process generally takes a lot less than making the material. We can account for that. The bauxite, the aluminum, the wheels have to be shipped around. We can account for how much that is. We can say put in quantitative metrics of how much energy it takes to ship a ton of material a given distance. And railroads are a pretty good way of doing that. And you've probably heard some of the railroad commercials that are touting what efficient ways they are of transferring things, and they truly are good. And then we use that wheel is going to roll down the road, and do it for wheels a little bit complicated, but we do it for an entire car easy enough, and say while you're using it, how much energy does that take? Actually, in the case of a wheel, every mile it goes, some energy has to be put into it to keep it going. And then in the end, there can be an energy cost for disposing it. There could also be an energy gain if you end up recovering it. And so this energy gain might be related to the embodied energy you have in the material. Okay, so it's a fairly simple accounting. We've got these 5 basic phases of the life cycle of the component: embodied energy, how much energy it took to manufacture it, how much energy it takes to move it around. This also means that stuff that's used in the USA, there's a great environmental benefit in producing it in the USA rather than shipping it from some far-flung country, because there's an energy associated with transport. Then we use it, and that's usually the dominant phase, and then we dispose or recover, and we'll go through a couple examples of how this can look. So let's look at the given products. So if we have an airplane, something like a civil airplane, and this is all on a fractional basis, the number of gallons of fuel that a 737 burns over its lifetime is amazing. It's swimming pools worth of fuel get burned. So if you can do anything to make that more efficient, it trumps everything else by a long way. Material stuff pales, manufacturing energy pales, transportation and making the airplane pale. They're all very small. So as a result of that, you can actually afford to do really lightweight materials, very expensive materials, and it will pay back, and I'll show that to you in a little while. So as a result of that, for civil aircraft, it makes all kinds of sense to use carbon fiber, high-strength aluminum, anything you can to reduce the energy burned over time. A car is similar, and we'll go through this in some depth. Here's the use energy. Again, this is the biggest part, and again, it's just fractional. Everything goes up to 100. But material content becomes pretty important, and we'll see that that becomes a big deal later on. Manufacturing is usually small. Transportation is usually small. If we've got an appliance, again, use is usually the dominant thing. If refrigerator is going to take energy over its life. Materials are usually relatively small, but not insignificant. It takes a fair bit of energy to make the aluminum, the rubber, the copper, and everything that goes into a refrigerator. But again, it probably shows that if you could, put a fair bit more energy and resource into insulation, you will end up with a refrigerator that's a little bit more expensive, but reduces the amount of energy used. In something like a car park where you're just making concrete and building a car park, there's really very little in use. Some transporting concrete around, some in pouring the concrete and all of that, but the material itself is the dominant thing. And we could choose not to use concrete. We could choose to build this out of wood, out of aluminum, out of steel, and all these different construction methods have very different environmental footprints. And also, particularly if you think about what happens after it, you can't really recycle concrete. All you can do is crush it up and do something else. Whereas if you made a car park out of extruded aluminum, when you're done with it, provided you could do that affordably, you could recycle it and basically capture all of that. So there are some very interesting things you could do with sustainable materials. Private house, again, now the insulation, you're putting heat into that. Again, a little more effort and money expended in insulation will probably pay off. But again, materials, concrete, wood, all that goes in are significant. And again, you could consider carpet. Again, it looks a lot like the family house again, and use might be just what it takes to vacuum on it. We'll talk about a couple more examples before we're done. So anyway, we can do an eco audit this way, and there are quantitative software tools that can be done that break all this up. If anybody is interested, I know that ASM has a very good relationship with Granta, the company that does this Cambridge Materials Selector. I'm sure if somebody in a K-12 environment wanted to use this tool, that a deal could be made, and there is great software, and it's not so difficult to use. The company Granta suggests using it for high schools, but it's not done that much right now. Okay, let me get a little more technical again. Again, logarithmic scale, embodied energy, and this is megajoules per kilogram, and you can see 1 megajoule per kilogram, 2, 1, 10, 100, 1,000, going up by orders of magnitude. And you can see various materials on here. Again, metals, polymers, ceramics, concrete. In the whole scheme of ceramics, concrete doesn't actually take that much. Concrete includes a fair bit of rock in it. Cement is the part that actually requires the energy. You see cement is up here. Takes significant energy to make it, but it's just when you multiply it by the volume of cement, that's where it gets to be such a huge energy user. So what this is how much energy it takes to make particular alloys. So titanium is a very, very energy intensive material to make. That's the greatest. Takes about 10 times as much energy to make titanium as it does to make stainless steels. Aluminum alloys, I want to point out, we'll do some aluminum example in a little while. That takes about 200 megajoules per kilogram to produce, and that's roughly 10 times as much energy as it takes to make carbon steels. Wood is grown, doesn't take much energy. You're harvesting natural energy, pretty low, which is mostly needed to cut it and cut it and ship it and so forth. Point I want to make with this is I think nobody's going to understand, nobody's going to memorize this whole table, although being a guy who's done materials for a long time, I kind of have an idea of where these things fit intuitively. But point is that we have these embodied energies in terms of how much energy, and this is really, could turn this into kilowatt hours, for example, to make a kilogram of material. We can be very quantitative about this. We can say exactly how much energy it takes to make aluminum versus steel and so forth, or concrete. So we can evaluate designs this way. Again, with polymers, you can see these don't change very much. So if you're going to make a polymer water bottle, that's the energy. And I guess you can see that there's a fair bit more energy embodied in making it out of polymer than there is out of making it out of glass, and that could be a good comparison. It takes less energy to make a unit of glass. A glass bottle is a little bit heavier, however, and it takes more energy to ship it and so forth. So there's a lot to be thought about in terms of comparing a glass bottle to a plastic bottle. And then certainly if you went to the old school model, where instead of remaking the bottle, you just sent them back, they were washed off and used again, you could make a good case that a glass bottle is actually much more sustainable. And that just shows as many materials that sit about at that level. And this is another version of this. This is, again, megajoules per kilogram production energy. This is production energy in megajoules per volume. So a material, for example, carbon reinforced plastic, you can see is fairly sits here relative to, and it has about, in terms of metal, similar value to aluminum alloys. If I take the same material, carbon reinforced plastic, you can see on a per kilogram basis, it's significantly higher than aluminum, and that's because it's a light metal, so you're just basically multiplying each thing by its density. So you can go on a density or a volume or a weight basis and find out how much energy it takes to make something. So anyway, we have this eco audit tool. You can take something. This is a heater that would heat a kind of industrial heater that might heat a room. You can take your user inputs, the software, use data for how much embodied energy there is for each thing, how much you have to ship it around, and so forth. Put it into an eco audit model and come up with graphs like this, and also come up with what the overall footprint is. And this can be based on energy, or it can be based on CO2 output. That's all basically in the software. And again, I'm not going to go through software here. So we can do this with, again, a water bottle problem, using this with a plastic water bottle. We can do energy, and imagine we're recycling. So in this case, the material takes a lot, manufacturer takes some. We ship this around. If you can reduce the weight of the bottle, that's good. It's probably not good practice to ship water around anyway. Not great environmental stuff. Use refers to putting it into the refrigerator and having it cooled. If you've got a material that has a very low coefficient, very low thermal transfer properties, it might be hard to cool it. And then disposal. This is recycling. We're assuming that we're getting some energy back by recycling. We're getting some of this embodied energy back, and it's less than it was here because we can't completely recycle the material. There's always some loss in there. This is a carbon footprint with recycling. Again, looks very similar, but it's just based on CO2 emissions. We could imagine that instead of recycling that bottle, we take it and we burn it, and we get a little bit of energy back if we burn that bottle. We're getting some of the embodied energy back, but again, not all of it. We could also do a carbon footprint and assume we burn it, and if we burn it, we're actually putting out a whole lot more carbon also. So again, the whole life cycle affects the carbon footprint on your decision to drink a bottle of bottled water that's in a plastic bottle. Kettle jug, you can see the biggest part of that is use. And again, if you can make this so it's better insulated, you're probably gonna make a more efficient jug if you for your use. So again, insulation is a good thing. There's not a whole lot of changing material for its own sake. Material is a small part of the whole equation. So to make this out of aluminum versus steel probably isn't a huge deal. Again, going back to polymers, you probably want to make that as something where the use temperature has a glass transition temperature is far above the use temperature. Otherwise, it's going to get too soggy while we're doing that. Okay, so what I want to jump to next is change topics a little bit. I'm going to leverage what we've done here, and let me consider start here and go back a couple of slides. But let me consider our friend the car. So this is early vehicles, Model T Ford, current generation pickup truck, slightly older version. These are very heavy structures right now. One of the most straightforward ways you can improve fuel economy on a vehicle is to make it lighter. Every time you accelerate, every time you stop, you're putting in a whole bunch, you're changing a whole bunch of chemical energy into kinetic energy, and that's reduce the weight of the vehicle, and you save quite a bit. So that's going to be the theme of this. We're going to try to be a little bit quantitative about this and look at different kinds of vehicles. So let's see. So it's kind of a heavy slide to get into, but basically based on this Ashby approach, what we can do is figure out what it saves us to reduce mass in a vehicle. Okay. So first of all, we need a proper metric. What is that proper metric? Well, the first one we think about is probably miles per gallon, and that's a pretty good one. Another one that you might care about, if you've got an airplane or if you're trying to justify your Chevy Suburban, is the passenger miles per gallon. You say, well, yeah, my Suburban only gets 10 miles per gallon, but I can put 10 people in it. So really, that's like 100 miles per gallon for one passenger car, and yeah, you can argue that that's a pretty good thing. Um, Energy per distance is another good way of doing that. That's just basically inverse of mile per gallon. That's basically the way they tend to do things in Europe. They talk about liters per 100 kilometers. Um, and liter has a certain energy content, liter of gasoline. So what I'm going to do here is I'm going to talk about and go use what Ashby uses here is talk about the energy it takes to ship a given extra mass, a given extra distance for some extra cargo. So what that turns into is usually megajoules of energy per ton shipped per distance. So kilojoules per kilogram per kilometer is another metric you can use with that. And let's use that metric. Again, that's if you want to do things with units and factor label method in your classroom, it's probably a good kind of thing to work on. So we can look at different kinds of shipping. Diesel ocean shipping takes like 0.15 to 0.3 kilojoules to ship an extra kilogram, an extra kilometer. Rail shipping is in the same order. If you go to a heavy truck, again, it's not so different, 0.3 to 0.4. If you do a personal auto, it's a little bit less efficient. You're carrying more in the way of your stuff, your so forth. If you use air freight, you're now talking about orders of magnitude difference between diesel and rail shipping. And if you ship something by helicopter, that's about the least efficient thing you can do. It takes a lot of energy to ship an extra pound, an extra kilometer by helicopter. And again, if you're doing the problems, you can convert energy into gasoline. Okay. Point is, there are really efficient ways of shipping things, diesel ocean, rail, and really inefficient ways of shipping things. So again, if you're trying to be eco-sensitive, to get something overnighted to you by FedEx, not a very eco-friendly thing to do. A lot of energy associated simply with shipping FedEx. So what we can do is we can multiply. So first of all, what we've done is we have transport energy here on a log scale, service life here on a log scale, and it turns out if you multiply these things together, here's a transport energy, here's a service life, we can figure out that energy times that service life, how much energy it takes, how much energy an extra kilogram of material takes you. And you find out that for a transport energy of 10 kilojoules per kilometer per kilogram and a service life of 10 million miles, this is sort of what you might get out of a 737. Turns out an extra kilogram you're shipping around costs you about 3,000 liters of fuel. Again, planes are fuel hogs. And it turns out you can justify about $1,000 on life cycle to pull a pound out of an airplane. If you do the same thing with a car, you find out, oh, you're in the ballpark of saving $1 to $10 by pulling a pound out of a car. So if you have extra stuff in your trunk, and most people do have an extra 10 pounds or so, that's actually costing you real money. That's going to cost you something like 50 bucks over the life of the car in terms of extra fuel just to cart that stuff around. So again, it's kind of doing the little things, but putting some math on it so you know about what it's going to be. And again, it depends a lot on these exact numbers, and you can come up with those. How far you ship that extra weight, how much that extra weight is, how efficient your vehicle is, and so forth. The other big point of this is we can also make some real decisions about how much value is there in lightweighting my vehicle? What's the value in terms of pulling 100 pounds out of my car? And we can do that by lightweighting the materials. So this is another kind of a complicated graph based on my friend log scale. This is just dollars per pound on a logarithmic scale along the middle here. Beneath here we've got different materials. Concrete is about the cheapest material I can buy. Steel sits in here. Magnesium is magnesium sits in here a couple dollars a pound. Copper, a few dollars a pound. These are all of our metals. They're in the order of $1 to $5 a pound. Affordable, but not cheap. Titanium, I think, is in here in the kind of $20 per pound sort of ballpark. Titanium we don't use unless we really have to. Carbon fiber is in the $50 a pound ballpark. Then gold is way up here, about $10,000 per pound. Okay. So that's on the bottom. On the top, we've got various vehicles going from cheap bicycle. You can go to Walmart, get a bike, might be made in a Chinese prison camp for about $2 a pound or so. Going to the most expensive vehicle you can get, sort of a vehicle, maybe like a communication satellite. You could make those out of pure gold almost. They're very, very weight sensitive. It costs a lot of money to ship an extra pound into space, and these have a very focused mission. Commercial jets, if you take the dollars you pay for a commercial jet, divide by number of pounds you got there, commercial jets sell at about $1,000 a pound, whereas an Accord might sell around $10,000 a pound. Okay, so part of the point of this is you really can't make a vehicle out of a raw material that's much more expensive than the finished cost. It's sort of a simple thing. So for example, if you're going to make a commercial vehicle, to make it out of carbon fiber is probably a non-starter unless you have a way of making it really cheap. However, if you make a Formula One race car, this is orders of magnitude greater than any of this, so we actually do see Formula One race cars that are made out of carbon fiber. So we can kind of understand that all on that basis. So let's take this to cars, and we will connect this in a little bit. So I'm going to take you a little bit through how we make cars and where it is today and where it might go and how all this fits together. And I think there are some possible nice stories you could use with your class on this. So real cars, this is the old Model T car that got us started, the first vehicle that really went mainstream. And Henry Ford, this was back in the idea where people questioned his business model because they thought, boy, who's going to have chauffeurs to drive them around? This is only going to be something for the very rich because you need a chauffeur in order to drive a car. That was the mindset at the time. Henry Ford tried to pay his people enough so they could actually buy their cars, and that was a revolutionary idea, and caught actually in that whole thing of manufacturing and trying to make things that make life more efficient is, I think, a big part of our standard of living today. But anyway, I digress. There's our Model T, and this was based on a ladder frame. This is like a 1930s wagon, again, based on a ladder frame. And basically what these are just two big steel tubes that go down from side to side. And that's the way we put the car together, with these big long steel tubes, and we put cross members across here. It makes for a pretty good platform, but it's not the lightest thing you can do by far. You need this extra frame, and on top of it, you've got to put this whole body structure. And also, these things are hard to make stiff. Stiffness is a big deal. So if you park on a curb or have this wheel go up, you want this thing to still define a plane, basically, and you want that plane to cant up on you, but that is going to tend to twist unless you really make this beefy or build some structure up on top of it. So stiffness is a big deal as well. The other thing that's a big deal is when you're sitting in your car here and imagine you come to hit a wall. If you're sitting in here, imagine that's a person, what you want is you want this area so it doesn't collapse on you. That keeps you safe. But you also want this zone to be able to crumple to absorb energy so you're not decelerated too quickly. So you really need different materials, different structure here. This you want to absorb energy. This you want to be as strong as possible. And that's not always easy to integrate into this ladder frame. So this is what we've done today to try to basically make a vehicle that's affordable and meets the criteria. And it's a pretty darn good thing. And this is a 2001 Jetta. And this shows the different kinds of materials. These are basically all steels. And you can see this cabin area here. This is made out of this very high strength steel, 1,000 MPa and greater. Megapascal is a unit of strength. Basically means it's very high strength steel. There's a manufacturing technology that was developed to make this very high strength steel. This is usually what's called hot stamped steel, or in modern vehicles we often make the cabin region out of hot stamped steel. And if you know enough of your physical metallurgy, what you basically do is take that steel, get it to the austenite state, and then you have dyes that are cold, and you form martensite, which is this hard, brittle phase on quenching. When it's formed and quenched all at once, and you can make these things that are called B pillars and A pillars. You form it and harden it all at once, you can make this very strong safety cage around you. But out here, you actually want modest strength. And you see this is under 220 megapascals, and that's to give you decent stiffness, but also give you something that can crush. And that's definitive. That's material selection. You select those materials for that property. The other thing you notice here is it's really been ingenious the way this all gets made. This is all based on a stamping process. Basically, you've just got fixed tools with shapes in it. And imagine this is a lousy drawing, but shapes in it, you put the steel in there, you crunch it down, you make these shapes between that. That's called stamping. And you use spot welding to stick these things together. Over the last 20 years, the main thing that's happened with automobiles is we've tried to make the material thinner and thinner and stronger, but it doesn't get stiffer. The cars could get more compliant, and we've also, in steel, kind of reached about as far as we can go. We just can't keep making it stronger and thinner anymore. And a lot of reasons for that. And a lot of it has to do with the stiffness of the structure. And also out here, you need some energy absorption. You can't use really high strength steel in the front because you need energy absorption and crash, and you need the same thing in the back. So it's a very highly constrained, very complicated, actually fascinating engineering problem that we have with this. And so there's actually a lot of work going on to figure out what are we going to do next. And there's people looking at exotics. If you're going to build a race car in your garage, you often do this. This is what usually we do, is do 4130 steel tube. You fixture it, weld them up at the edges, and you can make fairly light, very strong structures that way. Your roll cage keeps you safe. It may not necessarily have optimal crush and crash worthiness. This is triangulated tube construction is what this is called. And that's probably not going to work. It has a reputation of not being a very easy, not being able to make this very cheaply. If you make a real exotic, this is a Lamborghini. This is a carbon monocoque chassis there. And again, you bolt onto this front structure. This is where your crash worthiness. This is very stiff, very strong, helps protect you. And this is very expensive. At least $5 signs would go along with that. People are working on making carbon less expensive, but takes time. Lotus is a company that's done some very innovative things. They've got a long heritage of lightweight exotic race vehicles. These are aluminum frames. This is a backbone structure. This is what they call a punt structure, both made out of aluminum. And again, trying to get high stiffness. That gives you really good performance, lightweight, and also then you design the front end and so forth, so you have some crash worthiness on it. So these ideas are kind of permeating what the designers at places like Honda, General Motors, and so forth are doing. They're trying to figure out how to meld these ideas with reasonably priced construction. So this is sort of where we're going. This is a Volkswagen idea. And you see the next car of the future, we believe, is going to be multi-material. You see aluminum playing a role, axle components made of magnesium, very light metal, hardened steel, again, forming the safety structure, lighter weight, or lower strength steel out here that gives you some crash worthiness, some ability to absorb energy. But there's real problems with this. And people don't really make cars like this much at this point. Remember when we heard from Jerry Frankel about corrosion? If you stick dissimilar metals together, they tend to corrode. That's an issue. We can't spot weld aluminum to steel. That's an issue. Magnesium is a very brittle material. That's an issue. So it actually turns into a wonderful material science problem, and that's driving research into how do we design and make these things. But at the same time, we know we can reduce the weight of a vehicle almost by half, and that can really do a lot to improve fuel economy. So there's a big push based on sustainability and fuel economy to go this way. So this is sort of what we're doing. Is this multi-material approach is the best material for a job. Structural composites are really light. High-strength steel gives you this zone that protects passengers in the middle. Magnesium is super light. Aluminum has a great mix of strength and also is a very good energy absorber for crash. So that's what really the state of the art is in the automotive world right now, is trying to figure out how to marry these materials to make really sustainable next generation cars. This is an example of how things might be put together, where you have steel, aluminum, aluminum strut towers, magnesium die casting, and all kinds of processes and so forth have to come together, and we've got to be really clever about how we join these things. And again, welding often isn't an option. We've got to worry about these galvanic cycles and so forth. Okay, so now, kind of interesting. So what we have now is this might be made out of aluminum. We can take that and we can replace it with steel. Is that going to, in terms of the life cycle of the vehicle, save you energy? Is it more sustainable or not? Well, it actually all depends on how far you take and drive this vehicle. It really does. You have to do the math. That's what you end up finding. Because you see, for a family car, if you take a family car and you say replace iron with aluminum, imagine we're going to do that. Look at this part of this. This is the production energy for various materials. Here, my metal is here. My aluminum sits here. My steels sit here. And you see the steels take about 1/10 the amount of energy per unit kilogram per unit weight to do that. So actually, if I go and replace the steel with aluminum, my material bar is going to go up, but it will drive my use bar down. And many analyses have shown that, well, it's about a wash. So design matters, materials matter, and all this. And I think over time, and part of that, if it's a wash, depends on what happens to the aluminum when it's done. If you can take the aluminum out and recycle it properly, you do something that's actually quite a bit better. But if you just take it and landfill it, it's hard to make the case that aluminum is going to save you a lot. It's not going to do much in terms of sustainability, because you got to put a lot of energy in to make the aluminum, and then it does save you energy over the lifetime of the car. But whether it's enough or not really depends on this end of use decision. So anyways, sustainability is a tricky thing. You need math to figure it out. And again, I think this is all good stuff for for kids to know so that they can be really literate citizens of the world. That we need more people that think in math, not just adjectives. And that's it for now. Hope you've enjoyed things, and I'll be catching up with you through internet and so forth. And momentarily, that's my next thing to do right now. So hope all's well, and we'll finish up strong. See ya.